Welcome to P40 Enhanced 105 Control and Monitoring Training Module. Here is what will be covered in this module. Setpoint group. In this section, we'll introduce how to select the active setpoint group among four groups. Breaker switch control. In this section, we'll introduce how to control the breaker and switch. Pole discrepancy. In this section, we'll introduce two different ways of pole discrepancy detection. Breaker failure. In this section, we'll introduce the breaker failure relevant settings. Synchro check. In this section, we'll introduce the settings of synchro check. Code load pickup. In this section, we'll introduce the application of the code load pickup. ctvt supervision. In this section, we'll introduce a different method to check the CT and VT status. Pole dead. In this section, we'll introduce two ways of pole dead detection. And in the last monitoring section, we'll introduce these elements: circuit breaker arc current, circuit breaker health, current demand, digital counter, harmonic detection, loss of comms, and DC supervision monitor. And finally, we'll recap what we learned in this module. So now, let's get started. P40 Enhanced provides four setting groups. All settings contained under protection setpoints are reproduced in four groups, identified as group 1, 2, 3, and 4. These multiple settings provide the capability for both automatic and manual switching to protection settings for different operating situations. Automatic protection setting adjustment is available to change the setting when the power system configuration is altered. Manual switching can be done from the summary active settings and select the active group. All this can be done under the control setpoint groups and select the other active setting groups by using the operand. So for example, for the setting group 2, this can be turned on or by using the opto input or other operand. So when there's multiple setting groups enabled, the confliction in the selection of the active group between the active settings and the activation of the signal configured, the higher numbered group is made active. The active group status can be accessed as the device status path directly under the front panel or through the software monitoring device status active group. Some application conditions require that IED does not change from the present active group. The prevention of the setting group change can be applied by using this inhibit. So there's a 16 inhibit settings which can be block the change of the active setpoint group. P40 Enhanced can be used to control the circuit breaker. Before we talk about the controlling part of the breaker, let's review the settings of the CV setup, which is under the System CV setup. We can choose the CD status to be the both 52A and B, or only 52A, or only 52B, or none. And the auxiliary contactor can be set to the other operand, and here we're using the opto input 1 and 2. When opto input 2 is on and opto input 2 is off, the CB status will be closed. When opto input 1 is off and opto input 2 is on, then CB status will be open. If both opto input 2 and 1 are on or both off simultaneously, then the CB status will be unknown. Under the CB control, the first setting is CB controlled by. There are 8 options. From the first one is disabled. If no CB auxiliary contacts are available, then this setting should be set to disabled. And no CB control will be possible. The other 7 settings are the permutation of remote, opto, and local. There are 2 ways of local control. The hotkey allows the user to manually trip and close the CB without the need to enter the CB control menu or using the control menu CB trip close command. Here we're going to select this to opto plus remote plus local. The length of the trip and the close control pulse can be set via the close pulse and trip pulse time. This should be set longer enough to ensure the breaker has complete its open or close cycle before the pulse has elapsed. The default time are both 200 milliseconds. Manual close delay is used to operate the output contact following a time delay defined by this setting. One reason for this delay is to give the personnel time to safely move away from the circuit breaker following a CB close command. The trip command and the external command, they all can be reset to the CB closing process within this manual close delay duration. The CB healthy time is used to check if CB is in healthy condition after this delay followed a close command. Otherwise, we'll raise the CB unhealthy signal. And system check time is used to check if the check synchronization criteria are satisfied within this period following a close command when synchronism function is enabled. Initiate circuit breaker close and initiate close command are used to use any operand from the pull-down list to manually close or open the circuit breaker. Reset close delay provides a list of operands to cancel the CB close cycle before the main close delay expires. The close cycle can be cancelled by any trip. If an attempt to close the breaker is being made and the protection trip signal is generated from the setting of the trip command in or external in, then the protection trip command overrides the close command. CB healthy is the input for CB status healthy if CB closed in progress but CB closed 3-phase operand not satisfied after a CB close a healthy window, then man CB unhealthy operand will be generated. Man check synchronization is the input for check synchronism. It is only available for the voltage models. And CB trip close manual trip and close can be manually launched using the CB trip or close command, and this can be set to no operate trip or close accordingly. P40AE-105 enhanced support the switch status and control for up to 8 switchgear elements. This device is able to monitor the status and control up to 8 switches. The type of the switch options are load, brick, disconnector, earthing switch, and high-speed earthing switch. The status can be set with 52A only, B only, or both, like a circuit breaker. And this control can be set to local, remote, or both. The trip close command is to directly trip or close the switch by using the operand, and the output operand are SW1 control, TRP, or SW1 control, CLS. The switch auxiliary contact 52A and B define the signal that provides the status of the associated auxiliary contacts for each switch. When opto input 1 and 2 are used for the circuit breaker, then the other opto inputs can be used for the switch. The trip pulse time allows the user to control the width of the open and close pulse, and by default the time pulse is 50 milliseconds. The trip alarm and the close alarm time control the delay of the open and the close alarm when the final switch status is not in line with expected status. The status alarm timer allows the user to define the duration of the wait timer before the IED reads the status alarm. And the switch block remote ops setting blocks the switch remote operation, and reset data set to yes, then it will reset the switch monitoring data. The pole discrepancy element detects if one or two of the breaker poles remains open following close command, or if one or two of the poles remains closed following the open command. This element can be used for retripping the breaker after pole discrepancy detected. So the function can be set to trip, alarm, latch alarm, and configurable. The CB trip trigger setting assigns the CB trip initial signal. The CB close trigger settings assign the breaker closed initiation signal. The external poles discrepancy setting selects an operand as an input from the pole discrepancy detected externally by arranging the breaker auxiliary contacts. The time delay setting provides the definite time used to determine if the breaker status match with the breaker operation command. If not, then pole discrepancy is declared. This delay setting should be set longer than the breaker operating time. There are two ways of the detection of the pole discrepancy. There's a auxiliary status based and current based. In the auxiliary based mode, phase ABC open and close setting are used only for the auxiliary status based pole discrepancy detection. In the current based mode detection, the current limit must be programmed. If the phase current is detected below this current limit, then the pole discrepancy will be declared open. And if the current is above that limit, then the pole will be declared as closed. In the current mode, current limit must be programmed. If the phase current is detected below the current limit, then the pole will be declared open. If the current is above that limit, then the pole will be declared closed. The circuit breaker failures scheme trip all the backup protection breakers when the primary breaker failed to interrupt the fault current. When the function is set to retrip, then the scheme will be initiated by the phase or neutral current higher than the retrip supervision pickup, it immediately sends a trip signal to the breaker initially signaled to trip. In this way, it reduces the possibility of widespread tripping from a declaration of a failed breaker. This feature is usually described as retrip. The scheme determines the breaker failure condition supervised by 3 ways. The current supervision only, the breaker status 52B only, and both current and status 52B. Breaker closed selection the operand to indicate that the circuit breaker is closed. And each type of supervision is equipped with a timer delay, after which failed breaker is declared and a trip signal is sent to all breakers required to declare the zone. The delays are associated with the breaker failure time T1, T2, and T3. The timer 1 and 2 logic provides 2 levels of current supervision, the high set and the low set. This allows supervision level to change. For example, from a current which flows before a breaker inserts an opening resistor PIR into the faulted circuit to a lower level after resistor insertion. The delay interval between high set and low set is the expected breaker opening time. Different breaker manufacturer has different design of this PIR, so it is important to understand the sequence of the PIR operation during the opening before setting this parameter. Breaker failures can be initiated from the external initiation by using that operand list, or there's a 15 initiation can be chosen from the phase IOC, neutral IOC, etc. The synchronism check function is intended for supervising the parallel of 2 parts of the system which are to be jointed by the closure of the circuit breaker to avoid unacceptable shock to the system. If this feature is enabled, then the check will be performed before either manual close or automatic reclose the breaker. By default, the 3 VT are used for the bus VT, and the 4th VT is used for the line VT input. Synchro check will check the bus and line input voltage within the programmed differentials of the voltage magnitude, the sleep frequency, and the phase angle, different voltage. The time during which the 2 voltage remains within the admissible angle difference is determined by the setting of the phase angle difference delta phi and the frequency difference sleep frequency. When the delta phi is 30 degrees and the delta f is 0.1 Hz, then the calculated time will be 1.66 seconds. As a result, the breaker closing time must be less than this computed time to successfully close the connected both energized side. The sleep frequency hysteresis is used in reset of the synchronized element. Once the synchro check element has operated, the frequency difference must be increased above that sleep frequency plus this hysteresis sum in order to drop out. The synchro check programming can allow permitted closing if either or both sources are de-energized, and dead source permission provide this combination of the dead and live source that bypass synchronism check function and permits the breaker to be closed when one or both of these two voltage are below the maximum voltage threshold. And there are options of disabled, LBDL, that's for live bus and dead line, DB and LL, that's for dead bus and live line, DB and DL, that's for dead bus and dead line, DB or DL, that's for dead bus or dead line, and DB exclusive OR of the DL, that's for dead bus exclusive OR of the dead line. For these logic conditions, the live and dead bus voltage must be defined. So there are bus and line live voltage defines the minimum voltage source is live or energized, and bus and live dead voltage that defines the maximum voltage magnitude below which the voltage source is dead or de-energized. And sync bypass is used to set the operand to bypass the synchro check function, and inhibit is to choose operand to block this function. For example, to use the 52A when the breaker is open. The CLP code load pickup can block the IOC element and raise the pickup level of the TOC element of phase, earth fault 1 and 2, and the negative sequence overcurrent elements. When the code load condition is detected, the code load condition is detected during the closing of the breaker on a feeder that has been de-energized for the T code time. Then the feeder inrush current and motor acceleration current during the breaker closing may be about 500% of the nominal current and far above the pickup level. The IOC element can be blocked. For this block time is TCLP time delay. The pickup level of the TOC element can be raised to the new setting in this raise TOC apart. And after the time delay, TCLP time delay, then the normal overcurrent setting are applied and the CLP function are disabled. If any of the phase, earth fault, or negative sequence overcurrent, IOC, TOC element are not enabled, then that element will not be displayed in the setting of the CLP. So for example, now we have this block phase IOC available. If we go to the protection summary and disable the phase IOC element, and now come back to the CLP, we can see that the phase IOC block is disappeared. So the function must be enabled, will be shown in the CLP setting. The setting group can be assigned into different setting groups for this CLP element. And there's also inhibit, which can block this CLP operation. The CT supervision checks the CT failure, like the open CT secondary wire or a loose connection on the face of the three-phase CT banking wiring, which can lead to misinterpretation of the false current signal. CT supervision element use three distinct checks: the sequence check, differential check, and symmetry check. CT supervision can be set to trip or alarm. The maximum current supervision applies to sequence, differential, and symmetry check. It supervises each check function with maximum load current condition. If the phase magnitude of any of the three phases is above this setting, the respective check function is blocked. This avoids nuisance alarm under fault conditions and unnecessary blocking of protection element during faults. The time delay applies to all three checks, and this is the common delay settings for the whole element. The CT supervision checks the CT failure, like the open CT secondary wire or a loose connection on the face of the three-phase CT banking wiring, which can lead to misinterpretation of the false current signal. CT supervision element use three distinct checks: the sequence check, differential check, and symmetry check. CT supervision can be set to trip or alarm. The maximum current supervision applies to sequence, differential, and symmetry check. It supervises each check function with maximum load current condition. If the phase magnitude of any of the three phases is above this setting, the respective check function is blocked. This avoids nuisance alarm under fault conditions and unnecessary blocking of protection element during faults. The time delay applies to all three checks, and this is the common delay settings for the whole element. The sequence component check, which use the zero sequence current, zero sequence voltage, and earth current when it's available. Voltage must be connected in the Y configuration to be able to calculate zero sequence voltage. In the normal balanced condition, the zero sequence and negative sequence components are very small within the tolerance. In the fault condition, both 3I0 and 3V0 or IG will be above the pickup level. Then the element is not a CT failure condition. When one of the phase of the current disappears, if measured 3I0 be higher than the pickup and neither 3V0 or IG are higher than the pickup, the element is in the CT failure condition. The settings of the sequence 3I0 and 3V0 at the pickup level, and the sequence IN1 set is from the ground current input out for the sequence check. It must come from a core balance CT or a transformer neutral point grounding CT. A residual ground input method should not be used for the sequence check. If voltages are not available or they are available but in delta configuration, then the differential check can be used. The differential check uses calculated zero sequence current and earth current to calculate differential current. Under normal load and balanced condition, the ground current measured from the ground CT should be theoretically be equal to the calculated neutral current 3I0. In such condition, the total current difference ICT diff should be 0. With the CT supervision, differential current is higher than the diff current set. It can be concluded that the fault is either in the ground current path CT or one of the phase current path CT. A dynamic correction slope is used to compensate for higher CT errors at higher currents. However, the maximum load current supervision check is used to limit the CT failure detection during the real fault condition. Diff IN1 polarity setting, this is provided to allow the changing of the core balance CT polarity if the connections are reversed. If both phase CT I0 and core CT IG are of the same polarity, then diff IG polarity setting can be set to the same. If CT polarity are opposite, then the diff IG polarity can be set to reverse. The CT supervision element ground current input must come from a core balance CT The transfer neutral point ground CT or the residual ground CT method should not be used. If the earth current is not available, then the symmetry check can be used. The symmetry check operates by calculating the quotient of the ratio of measured minimum phase current over maximum phase current. Under the normal balanced load condition, this value is close to unity. If the quotient falls below the pickup level, it can be concluded that there is a fault in one or more phase current paths of the CT. This function should be set approximately considering the possible minimum and maximum load current occurred in various scenarios. The minimum current supervision is used to ensure that at least one of the phases need to be higher than the minimum value in order to detect CT disconnection problem. The voltage transformer VT supervision function is used to detect the failures of the AC voltage input to the protection. This may be caused by VT faults, overloading, or faults on the wiring, which usually result in one or more of the VT fuse blowing. There are two scenarios to a possibility with respect of the failure of the VT input: loss of one or two phase voltage and loss of all three phase voltages. The VT supervision logic is designed to detecting the voltage input failures are not caused by the power system phase voltage failure and automatically blocking the associated voltage dependent protection element. And VT fails can be set to alarm or configurable, and there's a time delay setting with it. For the first scenario, loss of one or two phase voltage, if the power system voltage are healthy, no negative sequence voltage will be present. If, however, one or two of the AC voltage inputs are missing, there will be negative sequence voltage present, even if the actual power system phase voltage are healthy. VTS works by detecting the negative sequence voltage without the presence of negative sequence current. So if there is negative phase sequence voltage present but no negative sequence current, it is certain that there's a problem with the voltage transformer, and a VTS block should be applied to the voltage protection elements. For the second scenario, loss of all three phase voltages, there will be no negative sequence quantities present, but device will see there is no voltage input. If this is caused by the power system failure, there will be a step change in the current. However, if this is not caused by the power system failure, there will be no change in any of the current. So, if there is no measured voltage on any of the three-phase voltage and there is no change in any of the current, this indicating that there is a problem with the voltage transformer, and the VTS block should be applied to the voltage element to prevent maloperation. For the detailed logic diagram of the VTS, please refer to the instruction manual. The pole dead feature is used to determine and indicate that one or more phases of the line are not energized. A pole dead condition is determined either by measure ctvt inputs or the CB status. For the P40D, when current and voltage dropped below the set threshold, then a pole dead would be generated. For the P14N, only current input will cause the pole dead signal. Opened breaker status will automatically initiate the pole dead condition regardless of the current and voltage measurement. This feature can be used to block operation of under frequency and under voltage element when applicable. In this demo, I'm going to show you how to create this pole dead from the current, then from the breaker switch. So first we can check this breaker status is closed. Three-phase closed. Now we can see that there's a little bit current applied, 0.2 amps. That's why there's no target message. If I reduce the current to 0, and now we should see this target message for the pole dead. Now this pole dead is on, so I apply the current back, and then this disappeared. And now if I apply the current but I turn off the breaker, so now this pole dead is on, and this is because of the circuit breaker is open. The breaker arcing current element calculates an estimate per phase wear on the breaker contacts by measuring the integrating the current squared passing through the breaker contacts as an arc. These per phase values are added to accumulate totals for each phase and compare to a program the threshold values for alarm. The initiation selections which operand to start the arcing current accumulation. The breaker opening has a contact separation and arcing 2 stages. In order to subtract arc current through the pure breaker mantle contact, a programmable delay is introduced between the initiation and starting of integration to prevent false integration. This interval should include the operating current of the output relays, any other auxiliary relays, and the breaker opening. For maximum measurement accuracy, the breaker operating time should be measured with the breaker motion analyzer. After the contact separation, the integration of the measured current continues for 100 milliseconds, by which time most modern breaker will have cleared the fault. The alarm level is the total arcing current in kiloamps squared cycle. Check the switchgear manufacturer specification to enter the accurate alarm level for this feature. The arc current values can be checked under this monitoring menus, the values of the arc current under monitoring and record. Circuit breaker, CB. Under records, circuit breaker, and CB1, that's for the meters of the arc current. From this monitor of the circuit breaker, we can also check the parameters of the CB health, and for this metered values, the setting is under the CB health setup. The function can be set to alarm. So for this CB health, this information is monitoring and analyzing the operation counts, arcing energy of the breaker current, arcing time, tripping time, closing time, spring charging time, and fault frequency count and time. So all these factors together reflect the breaker health status. There are 2 modes for this breaker health is detection and monitoring. The detection mode can be used to help set the pickup setting based on the historical true values. Just like the health report we have seen, the operation count, arcing current, energy of the breaker current, arcing time, tripping time, closing time, spring charging time are all measured, displayed under that the records, CB health. But the element does not pick up when in the detection mode. Under the monitoring mode, this is the normal mode, whereas measurements are analyzed and element may pick up accordingly. For the preset trip count, the operation count is able to give directly information by comparing it with the permissible operation number. And when the longer tripping time and the closing time can be provided as an approximate estimate of the trip, close, coil, or mechanical wear. Longer arcing time would suggest that loss of the dielectric stress in the arc chamber. The increased spring charging time may imply that developing of the problem in the motor and the spring mechanism. The increased arcing energy of the braking current may reflect the possible of the contact wear. If the breaker arcing current element is disabled, then the arcing energy is not calculated and this setting should not be used. The arcing energy set is the individual values for each trip and not the accumulated values recorded in the breaker arcing current. The lockout threshold is the number of the breaker operation lockout, and this setting can be disabled for the auto reclose when the repeated further fault interruption could not be guaranteed. And the frequency account is set a time period, and for this time, for example, the 1 hour or 3600 seconds, the breaker operate count, separate alarm or log out can be set. The current demand is measured on each phase and on 3 phases for active reactive power. Set points allow emulate of some common electrical utility demand measurement technique for statistical or control purpose. The measurement type can be set to fixed demand and rolling demand. They both calculate a linear average of the quantity over the programmed demand time interval. For the rolling demand, it is updated every minute and indicate that demand over the time interval just preceding the time of update. And the metered demand value is under the monitoring, measurement, and CT demand. And also you can have this power demand measurement too. P40AE-105 enhanced to provide 16 identical digital counter. Digital counter counts the number of the state transition from logic 0 to logic 1. Digital counter have a totally 16, and the counter are used to count operations such as the pickup of element, change the state of external contact, breaker operation, or the pulse from watt-hour meter, etc. So in this demo, we are going to set the counter up by up to input 1 and counter down by up to input 2. And we're going to use reset as input 3. Just do a quick demo. So to check the status of the digital counter, we're going to go to the monitor and check records and digital counter. And now if I turn on the counter 1, so if I turn on every time I turn on the switch 1, it increases the accumulated. So now if I turn on the switch 2, every time it decreases the timer. Okay, so now I have number 2. I'm going to use the contact 3 to reset. So that's we can see all these timers status change by using the opto input. And there's be more functions we can use the frozen, and we'll not do this in this simple demo. The harmonic detection has 4 harmonic detection elements monitoring the ratio of the second harmonic to the fundamental magnitude. When these values exceed the threshold pickup level, then harm DET start operand will be asserted. After the time delay, harm DET trip will be asserted. The operand can be used to block the sensitive element like a negative sequence over current during the transformer energization. The harmonics are updated every protection pass. The operation mode can be set to any phase, any 2, 3 phase, or average. When set to average, the IED calculates the average levels of the second harmonic and compare this level against the pickup setting. The average of the second harmonic follows an adaptive algorithm depending on the fundamental current magnitude per phase, and which must be higher than the current cutoff level. The loss of comms monitors the activity on the interface via the configured protocol for this interface. The communication status is set for each protocol. If the communication is lost, the enabled interface will issue the loss of comms event and operates the operand loss of comms start and loss of comms trip before and after the pickup delay. The interface can be set to serial Ethernet or both, and only the protocol associated with the selected interface are shown in the screen as options. The P40 are enhanced to provide 3 DC supply monitoring zones, Zone 1, 2, and 3. This allows multiple monitoring criteria, and each zone must be configured to correspond to either an over voltage condition or under voltage condition. A single zone cannot be configured to provide an alarm for both under voltage and over voltage condition. Typically, Zone 1 and 2 are configured for under voltage conditions, whereby the lowest limit is set very low, and Zone 3 for an over voltage condition, whereby the upper limit is very high. For each zone, the function can be enabled, disabled, and there's a lower voltage limit and there is a upper voltage limit, and also there is a inhibit to block this function. Now let's recap what we learned in this module. First, we started the Setpoint group session and we learned how to select the active Setpoint group, the priorities of the Setpoint group, and how to inhibit the change of the Setpoint group. In the breaker and switch control session, we learned the different options for the control of a single circuit breaker by using the IED menu, hotkeys, and the opto inputs, and other relevant settings. For the switch control, we used switch 1 as an example to introduce how to set up the switch status input, where to check the status of the switch, and how to control the switch and the relevant settings of the switch. In the pole discrepancy session, we learned 2 different ways of pole discrepancy detection: auxiliary status-based detection using 52A and B, auxiliary contacts, and current-based detection. In the breaker failure session, we learned the initiation of the circuit breaker failure, 3 different supervision conditions and their relevant timer delays, as well as a low set delay application with pre-insertion resistor of the breaker. In the Synchro check session, we learned the application of the Synchro check, the requirement of the VTs, and detailed settings explanations. In the code load pickup session, we learned the T code time delay and T CLP time delay 2 settings, and the protection element affected by the CLP, like blocked IOC and raised the pickup level of the TOC. In the ctvt supervision session, we learned the 3 distinct checks for the CT supervision: sequence check, differential check, and the symmetrical check, as well as 2 scenarios with respect to the failure of the VT inputs, loss of 1 or 2 phase voltage, and loss of all 3 phase voltage. In the dead pole session, we introduced 2 ways of pole dead detection by measuring the line current and or voltage by monitoring the status of the circuit breaker auxiliary contacts. And in the last monitoring session, we introduced the elements of the circuit breaker arc current, demand, digital counter, harmonic detection, loss of comms, DC supervision, monitoring. And that concludes this training videos of the P40 Agile Enhanced 105 control and monitoring module. Thanks for watching.